Hello, is that clear? Okay, great. So this is joint work that I did with Alex, who just spoke, and Krista Story. And the talk is, the kind of main title is The Cost of Universality. And the subtitle is a comparative study of the overhead of state distillation and code switching in color codes. So these are really topics that have come up a lot at this conference, and I think personally some of the most interesting work that has happened in the last few years. Much of it sparked by Hector Bombin, and I think this is a very important question. You know, state distillation, we have heard in many talks, is very expensive, and code switching in between 2D and 3D color codes is kind of proposed as a way of replacing that. And it's interesting to ask, does it actually help? Does it do a better job? So that's the goal of this talk. Okay, so back to basics. Error correction, what's the goal? Well, we want to trade quantity for quality. So we can encode a small number of logical qubits and a larger number of physical qubits, but at the same time, we benefit by reducing the noise strength in our qubits. And hopefully the goal would be, if we have some circuit that we want to implement in a quantum computer, that the logical error probability of each gate in the circuit should be smaller than 1 over the number of gates in the circuit, so that probably our circuit will succeed. Okay, luckily we have a threshold theorem, which tells us essentially that this can be done, and that the extra qubits that you need to introduce into your system shouldn't be too bad in some sense. But that's the theoretical sense. In the practical sense, you really want to know a little bit more detail about how big you're going to blow up your system size. Okay, so the error correction threshold, I'd like to go into a little bit more detail on that. That's going to be important for us in this talk. So in this case, well, I should have asked Alex how his buttons worked. Laser, okay, great. So here we have a small code that you can use for error correction. This is the Steen code, or the smallest color code. And you can ask the question for a given physical error strength, P, what is the logical error strength? And that's this black line here. And this code will be useful as an error correcting code if you have a noise strength which is below the intersection of these two lines. Otherwise, you're going to make things worse by using error correction. And of course, you can use larger codes, and this is where the error correction threshold becomes apparent. If you have a family of codes, for example, I've drawn the hex lattice color codes here. If you have a family of error correction codes, then you should, below some threshold value of error probability, physical error probability, you should be able to find a code family member which allows you to get arbitrarily small logical error rate. And it's often useful to think about some sort of near threshold scaling of the logical error rate given the physical error rate and the threshold. In particular, to give back of the envelope calculations, which I'll do in this talk. Okay, so something else that I think is really important is what kind of noise should we assume when we're trying to analyze these systems? It's very common to get a good feel for a quantum error correction scheme to imagine that all of the measurements that you make, your stabilizer measurements for your code, are implemented perfectly. This gives you really kind of unrealistic values for the error correction threshold. And it makes a lot more sense, I think, to go all the way down to the detail level of how will you actually measure your stabilizers. Probably in most schemes, you will introduce ancilla qubits. You will use basic gates to couple those ancilla qubits to the qubits you want to measure. And your noise model should really reflect this. So in circuit level noise that I'm going to talk about in this talk, for example, you could use this circuit to measure a XXX stabilizer. And in order to think about how the noise propagates, or how the noise works in this kind of a circuit, you should have a set of rules that replace each component of your circuit with some noisy component. So the rules are as follows. any preparation of a state will flip with some probability p, and when I say flip, if you prepare in 0, it'll go to 1, and if you prepare in plus, it'll go to minus, etc. Any measurement outcome that you obtain from a single qubit measurement should also flip with probability p. Any gate, any single qubit gate, should be followed by a single qubit non-trivial Pauli with probability p, and the same for 2 qubit Paulis. And by that I mean each of these, like x will happen with probability p over 3, and down here xx would happen with probability p over 15, because there are 15 non-trivial Paulis. Okay, so I'm going to focus on, well, we'll see, I'll focus on the color code, but first I want to start a little bit more zoomed out. So I want to think about 2D topological stabilizer codes, and I personally think that these are a very important family of codes. One of the most compelling reasons to consider these codes is that they have, in this noise model that I just described, the highest known threshold with an efficient decoding scheme, which is close to 1%. And they are also implementable in some sense in many experiments, because you can implement them by measuring geometrically local operators, and some of them at least have efficient decoders, like the surface code. So I drew this picture here. What I mean by this is each dot is a qubit, and the geometrically local measurement would mean that you would introduce a small ancilla and measure some nearby qubits by coupling them with C-naughts. Okay, so in these systems, these two-dimensional topological stabilizer codes, the transverse gates, which are automatically fault tolerant, the most useful gates that we could think of using, they don't have the full power of that we would hope for in a quantum computer. So in particular, as was shown by Ravi and Koenig, they have to actually be Clifford gates. And this is, you can think of this as a refinement of the Easton and Knill theorem to this particular case of 2D topological stabilizer codes. And I just want to, I think it's a beautiful argument. I just want to illustrate roughly how that works so we have some intuition for it. So why can you think about this coming about? Well, one way to think about it is that in these kinds of codes, you can have, you have string operators, which all of your logical Pauli operators can have support on. And you can also deform those string operators. So for example, here I've drawn a cross. Maybe this is the surface code. I've drawn a cross, and any logical Pauli operator could have its support entirely on this cross. I could also move the cross around. And the next argument that you could make is, okay, well, if I have some transverse gate U like this, the tensor product of single qubit unitaries, and I apply it to some to the system, and I consider the action of that on a logical operator P1, then I should think about how P1 is transformed by conjugation under this unitary, and that'll tell me exactly what the unitary does if I know what happens here. So to understand that, I can think about how that commutes, how this U P1 U dagger commutes with some other logical operator that I can have supported on some other cross. And of course, if I write this group commutator down here, this entire operator can only have support on the intersection of these two crosses, which is some small size and therefore below the distance. And because all of these operators down here were logical operators, when I take the product of them, I get a logical operator. And since it's a small logical operator, it has to be the identity. It can't be anything else. So just taking this relation and noting that this holds for any choice of logical operators P1 and P2 tells me that whatever P1 transformed into has to commute or anti-commute with all Paulis, and therefore it has to be a Pauli. So by definition, it's in the Clifford group. Okay, so zoom in a little bit more into the 2D color codes. So one reason to think about these codes is because they saturate this bound. you can get all of the Clifford group transversely. So why can you get the Pauli operators? It's pretty clear what they are. So you can see by looking at this code that all of the generators are even and have joint support, which is either 0 or 2 qubits. So all elements of the stabilizer group of X type will have even number of qubits in them, and there's an odd number of qubits in the total. So of course, these have to be, these X, Y, and Z on all qubits have to commute with the whole stabilizer group. They're not in the stabilizer group, so they are logical operators. C0, you can give a similar argument. Hadamard in this code, because the X and Z type stabilizer group are the same, it's pretty clear that when you apply Hadamard to all qubits, you just flip X into Z. So that's a logical operator. We're almost done. The last one might be a little bit less obvious to see. I'll talk about it a bit more in a second. But note that the lattice is actually bipartite on qubits, so you can color every other qubit black and leave the rest white. And if you apply to the black qubits the phase gate, this gate down here, and the inverse to all the white qubits, you'll find that this implements the logical phase gate. And this will be important, and it'll be even more important when we look at the 3D version. So I'll just run through this argument a little bit. So why does this happen? Well, you can, as was in previous talks as well, you can think about the logical 0 state of a CSS code by applying essentially summing over all of the X-type stabilizer elements and applying that on the all 0 state. And this will just project onto the ground space. And if we think about each one of these X-type stabilizer elements, then they have a very nice property in this code. So if we think about, for example, a single generator, it's clear that it has 3 black qubits and 3 white qubits, so that they're equal. But actually, if you take the product of any of these, you find that they always have an equal number of black and white qubits modulo 4. And this really comes from the fact that any pair of stabilizer generators intersect on an edge here. So really using this, and also using this commutation that if you pull this rotation gate through X, you flip the sign of the rotation and you get this global phase out the front. You can just see by applying this gate to the 0 state that every time you pull the gate through a stabilizer, then you will always get a phase which is 1 because of this rule up here. Okay, and then it's pretty easy to see that applying this gate to the 1 state, because there's 1 extra black qubit than there are white qubits in this lattice, you'll get an overall phase. You'll get a cancellation except for 1 site, so you get this overall phase. Okay, cool. So how do we, so we have the color code. We know we can't use transverse gates in any 2D topological stabilizer code, but we want to use these codes because they have very good properties. So how are we going to do non-Clifford gates? Well, how have other people done non-Clifford gates? For a long time, people have thought about using cat state method, and that goes all the way back to the start of fault tolerance. And another way is resource state distillation, which we've heard a lot about here. Some other more modern techniques that have arisen in the last few years. So there's code switching. You can start in this code that you want. You can use some other code, in a sense, as a resource and switch to it. And that other code may not be restricted to having just Clifford gates, and then you can use that code to apply your non-Clifford gate and come back. There's also some other cool ideas. So multiple partitions, you can essentially think about you can generalize your notion of transversality, and instead of just allowing single qubit unitaries, you can allow coupling of multiple qubits, and you can actually get around these some of these no-go theorems. And peaceable fault tolerance, which came up in Ted's talk, is also another way that you can get around these. But as far as we know at the minute, although Ted hinted that there might be some progression in this direction, the only known ways to use any of these techniques for topological codes are distillation and code switching. So that's why I'm focusing on those two things in this talk. And moreover, the only known topological codes in which both of these things can be done are the color codes. So that's why we're focusing on color codes. Okay. So both of these you can think of in terms of resource states. So this is pretty standard. But if you have a T state which cannot be produced through Clifford operations alone, then it's possible to use that T state through gate teleportation to actually apply the T gate, which is a non-Clifford gate, to whatever state you want. So in this picture here, we're imagining that these wires are actually encoded qubits stored in, for example, the 2D color code. So only Clifford operations are allowed on those qubits. And this is all these circuit elements are Clifford. But we are inputting some state that we get from somewhere else, which is not produced by Clifford operations. And so both magic state distillation and code switching are ways to produce that state, that resource state. Okay, so I want to explain a little bit the basic ideas of each of these two approaches. So state distillation, basic idea, or one approach to state distillation is you use another error-correcting code on top of the one that you already used to design a protocol, a Clifford protocol, to take noisy magic states and make cleaner magic states. So I just want to illustrate roughly how this works. So again, each wire here is an encoded qubit in, for example, the 2D color code. And then this encoding circuit here is a Clifford circuit which encodes into some other code. So it's kind of a concatenated, we're imagining some sort of concatenated picture here. And in this other code, the T gate should be transverse. And if the T gate is transverse, then we can apply each of these T's by using our resource states, using the circuit that I showed in the previous picture. And then we decode from our code again, and provided that this outer code, this bigger code, had no faults, then our error should be suppressed, because this will only, if one error happened, we would detect it by this decoding procedure here. So this is roughly how magic state distillation works in this approach. And how do you actually use this? Well, you could start by having one unencoded qubit, physical qubit in your system. First encode that, well, first create the T state. It's unencoded, so you're allowed to do whatever gate you want. Then encode that in some relatively small color code. Do this a bunch of times. Take all of these, now encoded noisy, because this was non-fault tolerant, this encoding procedure. All of these will be noisy, but then you run this circuit on these color codes, and you get some output, which is again a color code with a T state, which is less noisy than these ones. So some P1, which is less than the original. And then you just repeat this procedure as many times as you need until you get as good a T state as you need for your computation. Okay, so because Jungwon talked about these really cool new ideas, I thought it might be useful to repeat his setting the scene of what are the different types of state distillation a little bit. So the first one that I just described is depicted here, but I've used slightly different notation so I can be a little bit more general. I want to name this unitary gate the resource rotator, which takes some stabilizer state into the non-Clifford resource state. And so, for example, what we looked at before, the resource state was T state, and the rotator was the T gate. I also want to introduce a Clifford, well, ought to be Clifford, resource stabilizer, which acts on the resource state and gives you back the same resource state. And so one approach is the one we already talked about. Another approach is you could imagine just starting your all of your qubits in the resource state, and then the distillation code, if it has the resource stabilizer as a transverse gate, then that initial state is an eigenstate of this operator. And then if we simply decode in this from this distillation code, then because this is a logical gate of the code itself, provided we happen to get the +1 eigenstates of the code afterwards, then we automatically are in a code state and an eigenstate of the stabilizer, so we have the resource state. And again, you get error suppression given by the distance of the code. Problem with this is that, so this is the one that Jungwon kind of brushed aside, because this, even if all of the initial states are perfect, then the decoding will only pass with some finite probability because the original state is not a code state. So then the other method, which is really what Jungwon was talking about, and also Cody Jones and Meyer, Easton, and Knill did, is this approach here, where it's kind of, in some sense, a combination of both. You have a distillation code, which has a logical resource stabilizer, and you also note the property that resource stabilizer can be written in terms of some Pauli conjugated by the resource rotator. And then you can use this circuit to actually check. If you have some input resource state, then you can use this circuit to check after encoding if the resource state was correct, and you will get error suppression on these gates which you use to do that gadget, and you'll also get error suppression on this. But you need to repeat this in some clever way, and that's what the outer code that Jungwon was talking about was. The reason is because, even if this works perfectly, if this is faulty, then you get much lower sensitivity to this in one go. Okay, so the kind of game in magic state distillation, in some sense, is finding these distillation codes which satisfy this, but also that have other good properties like high encoding rate, high distance. Okay, so 3D color codes. Sorry, I know there's a lot of just telling you things. The 3D color codes are similar to the 2D color codes in some sense. So here I've drawn the 15-qubit Reed-Muller code in big. It should be a little bit more familiar to people, even if you haven't seen too much of 3D color codes. But the idea is that instead of having stabilizers being defined as X and Z on faces, you now have X on volumes of the lattice and Z on faces still. And as a reminder of what we did before, so we expanded for the 2D color code the logical zero state in terms of the X-type stabilizers. And now in this case, we have a property where when you again do the bipartition of the lattice, the black and white qubits are equal for each element of the X-type stabilizer group, but now modulo 8 rather than modulo 4. And this allows you to apply a transverse T rather than a transverse S gate. But the argument is essentially the same. And now, why does this work? Why is this better in some sense or different from the 2D case? Well, it's because any three stabilizer generators now intersect at most one edge, at 0 or 1 edges. Whereas before it was just two stabilizer generators intersected at 1 edge. So that's essentially where the property comes from. Okay, great. So you have a transverse T, and you can, as has been discussed in this talk, you can switch, or in this conference, you can switch between these 2D and 3D codes as follows. So here. This is, again, using the 15-qubit code as an illustration. And so if you start in the 15-qubit code, the stabilizer group is X on volumes and Z on phases. And you can choose, there's lots of choices of logical operators, but let's imagine our logical operators being supported in the right facet of this lattice. And you can slowly switch from this to another code by sequentially measuring stabilizers and correcting them when they go wrong. So the first one is just measure the face here, so all x's on that face. And if you get a +1 outcome, you move on. If you get a -1 outcome, then you can apply, if you see the face here, which is shared between the red and the blue volume. So if you apply all z's to that, then you will obviously correct this face after you get a -1 outcome because it anti-commutes with that. But importantly, because this was actually in the stabilizer group of the code that we started with, it doesn't change anything else. And you can just keep going with this until eventually you end up with two decoupled sets of qubits. The right one is now the Steen code in this case, but more generally it would be the two-dimensional color code. And yeah, it's really amazing that this can be done. And I think it's pretty straightforward. Okay, you can do the same thing going backwards and forth. It's pretty straightforward to imagine how you would then use this to create a T-state. You start with a 2D color code. You know in that 2D color code, you can use Clifford operations and prepare an encoded plus state. Then you use this process just described to switch to 3D. And in 3D, the T gate is transverse, so you apply that, you get the T state encoded, and then you switch back, and now you have the T state in the 2D code just as you want it. And this should all be suppressing errors as you go. Great, okay, so the goal, we want to think about which of these is more expensive. Now we know roughly what they are. And I think it's important to have a picture in mind and note some of the key differences of these. So the 2D case has this real significant advantage that you only ever need 2D geometrically local operations for magic state distillation. In this case, using the 3D color code to switch into, you have to imagine that you have an architecture which really allows you, at least in some region, to do operations which are not geometrically local in 2 dimensions. And that could be a pretty big price to pay. So, you really, for this to be worthwhile, you either need an architecture that doesn't care at all, or you really want it to be much cheaper. So you can take the hit, essentially. Okay, so what are things that kind of make it difficult to do this comparison? Well, first of all, we need a circuit level analysis of the 2D color code using an efficient decoder. And as Alex was describing in his talk, in the previous talk, these can be done, and it's possible to do that, but not so much analysis has been done on the case of noisy measurements as well. And then another thing that needs to be done is distillation analysis using noisy circuits. Usually, distillation is, well, most commonly, distillation is analyzed by assuming that all of the Clifford gates are perfect, but this isn't true, and there has been work done on this, and it's definitely possible to analyze. So that shouldn't be too problematic. The next one, I think, is starts to get harder from here on. So circuit level analysis of the 3D color code. So Alex just mentioned in the previous talk that they're currently working on getting a decoder which can handle noisy measurements in the 3D case, and that would be really great. But unfortunately, that is not something that is can currently be done, or is currently known exactly how to do. So that's very kind of tricky. And then the last part is, so we need to think about efficiently, this process, I kind of brushed under the rug some of the stuff, but we need to think about efficiently switching between these codes. How do you know what correction to apply? how tolerant is this procedure to faults, and Hector has some, in the phenomenological case, some analysis of that, which helps convince you that it's definitely possible, but doing it is hard. So, okay, I'm lucky because Alex described the 2D noise-free decoder, so I'll very quickly just show pictures and say what's going on here. So in this case, we start with a 2D color code, and we imagine these black dots are physical X-type errors, and then the highlighted, so the brighter colored faces are violated stabilizers. And then, as Alex described, Nicolas Delfoss's decoder is basically to split into 3 subgraphs, where each subgraph excludes one of the 3 color faces. And then within each of those subgraphs, you can do matching whatever way you want. And after you put them all together again, at least in this case with boundaries, which is slightly different from what Alex talked about, you're guaranteed to have closed loops. And then the final step of the decoder is to either apply X's inside or outside the set of closed loops. It partitions the qubits in 2. Okay, and so we need to go to the noisy measurement case with this. So there are ways of thinking about this. There was some previous work by Ashley Stevens on this, and roughly speaking, what you do is similar to what you do in the surface code. You repeat measurements, and you look at differences in measurements rather than absolute failures of measurements, and then you do some sort of matching. So that seems schematically straightforward how you would do that. Something which it becomes problematic, as Alex hinted at, is for the color code, you need to do these 3 subgraphs separately, and then you need to put them back together again. And when they don't match up, you don't get the closed loops, which you need in order for the decoder to work. So what we found when we thought carefully about Stevens' decoder was that actually the way that it was technically described doesn't have a threshold, because what Stevens did was suggested taking D, so if D is the distance of your code, taking D time steps, and for each set of D time steps, collapsing them to 1 time step, and then applying the standard decoder. But if you think about it, if D is large, so in particular if D is larger than 1 over the error probability, then you will end up collapsing, almost every qubit with high probability will have had an error, and so you'll have just a mess after collapsing, so it won't work. Anyway, so what we did is we instead took connected components after matching and collapsed each connected component to a time step and dealt with it that way. So that avoids this problem, but and it can be done, and you can get some analysis of the logical error rate. Okay, distillation overhead, I probably don't have too much time, so I want to go pretty fast. But you can work out, you can basically incorporate the noise from the circuits that you're using to implement the distillation circuit, and also the underlying error correction, and the fact that the T-state distillation is noisy in itself because you're dealing with noisy T-states, and you can get some reasonable estimates of what the overhead is from that. And so here I wanted to go into a little bit more. How long do I have, sir? 5 minutes? Okay. So I want to go into a little bit more detail about this switching procedure. So in order to reliably do this with noise, you have to first prepare the plus state, and that will take d rounds of error correction to ensure that you've got a reliable state. So that takes d rounds. Then whenever you want to measure in order to code switch, you should again measure the new stabilizers for d rounds, because you won't, the first time you measure, there might be errors in the measurements themselves, so and that could really destroy the whole thing, because if you get the wrong measurement outcome, you'll apply the wrong gauge fix, and you'll actually you can introduce a logical error. So you have to be very careful to do that fault tolerantly. And then the actual this is probably not too difficult problem, but the actual calculation of what the gauge fix should be in terms of the outcomes is also something that should be efficient to calculate. And then you apply the T-gate, that's one time step, so that's the easiest part. And then you have to go back again, and the problem is kind of the same. But again, the kind of key point is that the probability of succeeding in this process, you can kind of estimate by how many time steps you spent in the 2D color code and what the probability of that succeeding is in each time step. And then the number of time steps D that you spent in the 3D color code and the probability of that succeeding. And so that gives you an estimate of the overhead there. Okay, so finally, the overhead comparison. So I mentioned this. It's pretty annoying that we don't have the ingredient that we really need to really pin down what this estimate is. We don't know the error rate of, so this is because we don't have a efficient decoder yet for 3D color code. We don't know the error rate of the logical information in the 3D color code. But what you can do is you can say so I'm maybe being too weak in my statement here. It's really not going to be better than the 2D error rate. Simply, there are many arguments that you could make for this. It's almost certainly going to be worse than the performance of the 2D color code. There are far more errors, far more qubits. There's many more things that can go wrong. But the operators are string-like, so they have many more wiggles in 3 dimensions than they do in 2. It's almost, and the weight of the generator is much higher, so it's very implausible that you would have better performance of 3D than 2D color code. So let's just set the 3D color code to have the same performance as the 2D to get some plots. So what you find, unfortunately, is that for the case of code switching, you have higher overhead. This is at 1/10 of the 2D threshold. So Austin Fowler would say this is unreasonably low error rate anyway. But so at 1/10 of the 2D color code threshold, you see that there's basically no regions where code switching is lower overhead than distillation. If you go to even lower overhead, so Austin's probably terrified now, but you do see some crossing. So it's not impossible that you could get some comparison, but I would remind you that it's very probable that this is much worse. And the threshold, if the threshold of the 3D color code is even half of the 2D color code, then this line, this curved line, goes way up. So it's kind of, I would say, an unfortunate comparison. What are you, sorry? Axes. Oh, sorry. That's very bad. This is number of qubits, and this is the log base 10 of the desired error rate of the magic state. Yeah, sorry. Okay, so yeah, I would say that these are kind of, in some sense, bounds. They're not really bounds because none of this was rigorous treatment, but in some sense bounds. And they also apply, because we didn't actually know what this was, and it's the only thing that really differs, they also apply to these kind of flattened schemes like Cody talked about, simply because the number of qubits scales roughly the same as it does for the 3D color code. You get a factor of half benefit. Okay, so to conclude, sadly, it seems code switching is, at least as is at the minute, is not much better, not as much better as you would kind of hope to compensate for the difficulty in going to 3D compared with state distillation. But you know, there were assumptions that I made that I didn't go into that could maybe make state distillation look less appealing. For example, you could imagine that it's hard to do long distance C0 and things like that. I did not account for that. That would make distillation worse. So that's important to remember. Yeah, okay. Something I think is kind of important and maybe not super surprising is that the hex lattice circuit level threshold that we found, and we didn't do a very careful job of optimization. You probably improve upon that. Is not crazily lower than the surface code, and this maybe shouldn't be too surprising given other recent results for other codes. Great, so more ideas for alternatives to magic state distillation are in order, I think, as well. I would conclude from this. Okay. Just before we go to questions as well, I have an advertisement. So, yeah, I'm at Microsoft in Redmond, and wow, censorship, yeah. So I'm at Microsoft, and Microsoft are hiring. I'm going to be available to chat all the time, of course, but I'm going to be at the Microsoft have a desk outside to chat if anyone wants to ask what it's like to be a postdoc in our group or anything else. And yeah, you should swing by, and you can also talk to Tyler if I'm not there. Okay. Thanks.
All right, thank you, Michael. We have time for some questions. Any questions?
Just curious to know if you have any circuit level simulations of the 2D color code, so logical error rate versus physical error rate.
Yeah.
You didn't present any? Do you have any?
We have some for the small distances here.
Sure.
Maybe I kind of didn't, I might have gone too quickly on that. It's annoying. Yeah. Do you want to continue asking the question while I find it?
Okay.
So we have, oh, it's further down. Yeah, here.
The reason I was looking for it is just to see what fraction of the code distance you can get out of the 2D color code using that decoder.
What fraction of the code distance you can get from this?
Like a distance D code suppresses really how many errors?
Oh, it's a good point. Yeah, unlike the surface code where you can cleverly design your circuits so that the bad errors that propagate to multiple qubits don't contribute to logical errors very badly. The color code has no such luxury, but you still get pretty close. So I don't know the answer to your question. I don't know what if the effective distance is compared to the actual distance, but I don't think it's much lower. Yeah.
Have you considered hybrids of the two approaches, and would there be any advantage to doing that?
It's a good question. I think, yeah, I haven't considered in detail, but I do think it's a good question because you would presume that in some regimes, code switching does better. So maybe it could be replace the first stage of distillation or something. I think that's a good idea, but it hasn't been explored by me.
Are there any other questions?
You talked about the overhead in space, but is there also an overhead in time to be concerned about? And
yeah.
then do a comparison there?
I think it's a really good question. So I didn't include it because it makes the picture worse for the code switching. Basically because the distillation circuit doesn't actually care, at least in this picture where you're doing everything transversely, doesn't care about the distance of the codes. The length of the circuit is the same. Whereas the code switching does. You have to wait for D rounds before you switch and switch back. So it actually, you pay a penalty in the code switching case there.
All right.
Thank you.
Well, let's thank Michael again, and let's thank all the speaker of the session.